Hello, everybody.
And so now floor is yours, and please introduce yourself.
Okay, thanks you very much, Leah. Okay, hello, everybody. Thank you very much to the Observatory and to you, Leah, for that invitation today. So my name is Alexander Kmoch. I'm a research fellow here at the University of Tartu in the Department of Geography. And I have the pleasure today to talk about myself, like all scientists like to do. And the topic of the presentation is sort of aimed at the geospatial for hydrology. And it's the background of EstSoil-EH, of the new soil dataset. So I did my master's and my PhD in geoinformatics in the sort of domain of spatial data infrastructures for hydrology or hydrogeology. So this is my background. I'm neither a remote sensing expert nor a hydrologist nor a soil scientist. I'm sort of first and foremost sort of a geospatial data specialist as such. Currently, I'm a Marie Curie fellow, and my research topic is about parameterization, sensitivity analysis, uncertainty analysis of spatial data in relation to hydrological modeling, in particular with the SWAT model. In addition, I'm always really active in geospatial or GIS associations and activities. I really like to spread the word and to be of value for other people who need GIS and geospatial. So we, University of Tartu, are also a member of the Open Geospatial Consortium, which is an international consortium of many hundreds universities, government agencies, industry sector, to advance geospatial data standards for data exchange, etc., metadata. And we are also a member of the Association of Geographic Information Laboratories in Europe, the AGILE. This might be quite useful. The AGILE in Europe is really an association in regards of research and education in geospatial, and they also really look around, everything remote sending is closed and so on. I've been co-hosting, co-organizing here hackathons here also in Tartu with NASA and ESA, also with our friends here from the observatory. And I do also several courses, or I teach in several courses that somehow work with GIS, geospatial data. Okay, so maybe at first a little bit background for the Estonian Soil Map. So as I introduced, all I ever wanted in Estonia was a soil data set, that is somewhat usable, has the variables that I needed, and that is sort of open in the way that I can share, and do this whole reproducible approach, so I can, share my experience and also my frustrations if something with the modeling doesn't go well. But somehow reaching out, there were some projects that work with SWAT, but the way they prepared the soil data was really difficult for me to trace and to redo for my catchment. So eventually I just started to work on the Estonian soil map to get out of it what I really needed. So the Estonian soil map, from the is available at the board Estonia, at the MAAMET on the website, and it is an open data set, and it is a really high resolution data set. And so in a way, it's really great to have that. And the main things that are sort of directly accessible and usable in the Estonian National Soil Map is the so-called color, the verf attribute, which is sort of a grouping that comes sort of historically. And then over time, those Estonian soil classes, the Muller type, they're sort of sorted in those groups, and they're those classical soil types that are agricultural soils, forest soils, grasslands, flat soils, and so on. Then this soil type is this cipher. Then another really important thing is the soil texture. So while the soil type, the cipher, classify sort of under which sort of regimen or which general sort of ecological context this soil is, if it's waterlogged or if it's a forest or an agricultural soil. The other thing is the soil texture, which describes the sort of granularity of the soil. And this is really important for hydrology because it really sort of influences, how quickly the water can seep through. So then there's some other attributes in the original data set that are a bit tricky to work with because they are also encoded in specific ways. The other important thing that is currently really, really used is bonität, the fertility, for land evaluation purposes and agricultural potential. So, and if we have a look at the original data set, because as I really needed to get sort of actionable numerical classes that are sort of easy to deal with in a modeling context, I can click this thing here, can I? So, as you see here, the soil types, they are those soil classes, but if you look at the larger picture, they are actually really highly specialized, and that it makes it really difficult to sum them up in classes. However, a soil expert, of course, can directly interpret those. Then the other thing, the texture, this would be the texture. This is really interesting. It is really highly specialized information. It tells you how deep it is, what type of coarse fragments, what type of texture, sand or it is in there, but it's basically impossible to actually get those numerical values out for yourself. And then bonität is a nice numerical value. This is good. You can make nice maps and nice analysis with this. And then you have the sort of organic horizon and additional information about rock content and so on, and this Werf, this class, this sort of summary class. So in terms of history, I mean, maybe some of you already know. I know that, for example, Might has worked, of course, with the soil data also for a long time, I'm pretty sure. So others, so many of you also know the soil map. Just a quick sort of historical background. So the first large-scale mapping was actually already launched after the war. And in the Soviet times, then also was a lot mapping because for the assessment of agricultural potential, basically, because it was in the end it was basically all about being able to have the crops properly planted, and then later also forest and other surveying was added to the soil map. And then in the 90s, the Estonian Land Board manually transferred about half of the soil map to cadastral maps. So then is when it really started to take off, and that the soil map was then digitized. And then the first final digital soil map was actually available by the end of 2001. And the classic GIS process is the paper maps, the historical papers were scanned, and then the soil contours were digitized, and the attribute data had to be transferred by hand. So obviously this is a very, very involved process. And if you look at an image of the historical map, then you can see, you have all these little polygons here, and you have this attribute data. Again, this is exactly this texture here, where you see the way this is basically now numerically and with these string codes, the loimes, the texture in the database. And as you see, there is a coloring scheme involved. So there's some yellow and some brown. So this is what then became this Werf, this color grouping. Okay, but coming back to what I actually needed was a machine-readable digital soil map where this wealth of information is accessible, in a way that I can run, model physical processes with it. So the tricky bit was really to be able then to use this data to predict, for example, hydrological processes, soil process, gas fluxes, all these things where you need particular things like a texture class or organic carbon content, hydraulic conductivity. So, and in order to be able to retrieve those, there I started to work on EstSoil. So, and the process overall is a bit like that. That is described now also in the paper. We've been working really long and really hard, I think almost 1.5 years at least, if not longer, on this data set and on this paper. And so at first we of course, extract all these text strings, and then we add additional information in data assimilation, data fusion methods, the various DEM variables, drainage, topographic data like land use, and then we build a machine learning model to predict additional variables such as soil organic carbon, bulk density, saturated hydraulic conductivity. And another thing that I really need for SWAT was available water capacity. This is also called plant available water. And this I assimilated from another project, EU Hydrosoil Grid. So this is sort of what is the main process for was creating this soil data set. So soil types. If we go back to what is the classing and the site, the University of Life Sciences here, Marie Curie, and the Land Board also has a soil legend handout. They describe about 120, 130 distinct soil types, and roughly basic textures, soil textures. So those are sort of the basic things. Now we know that, I mean, soil is one of the most complicated, complex things. Like if you have one handful of soil, the diversity of stuff that is in there is quite astounding. And so of course the scientists who really work with it, of course they love to be able to really, really finely and well precisely describe those. But this makes it really hard again for, let's say, a bit higher level analysis where you need to generalize and classify a little bit, where you can say which things are more similar than others. So where we said that we would only have 120, 130 distinct soil types, the specializations of those are around 7,000 different specific descriptions, because each soil polygon here is a little bit more like that, and then there's a different additional attribute, how glaic it is, for example, if it's a bit wetter than another place. And for soil textures, although basic soil textures are really only a handful, which is generally nice, the way they are, of course, described, the textures for each soil polygon is a mixture of depth information, of the texture class, the Estonian texture class, and rockiness or stoniness. And the variation is basically exponential. That's why this is basically nothing you can immediately use. So the first thing was then to generalize the soil type. And for that, I basically just try to find the best suiting from the handouts, from those 120, 130 defined ones, well-described ones, to find the best matching from what the text gives, what the code gives. So if you look here again, you have here some special types, and there might be a more generalized basic types in which category those can fall in, and then so the first step, the algorithm would just use those. So, and then there will still be a lot of issues, of course, that would not be sort of recognized as such, but a basic simplification basically already finds 98% or found 98.4% from those basic 120 soil classes. And then there are some that are really, really strange, sort of that might be caused by transcription errors when they digitize it from the soil map, or some other things. And then I would sort of have a lookup table to try to fix that, so that every soil polygon has a soil class from the official legend, and that is a smaller number of those. And the second thing important, if working in the international community, let's say we would want to have some joint soil information system for Europe, as we have, then we would have to map the Estonian soil types to a sort of agreed upon international soil classification. And the most widely acknowledged and accepted one is the World Reference Space, the FAO-WRB. And so we basically made a mapping table together with Arno Kanal and Ala Astove from University of Life Science that would map our standardized, from our 120, 130 standardized soil classes into the FAO classification. So that can then also be used if you as a scientist want to use, or as a consultant or whatever want to use EstSoil, then you can also rely on sort of the international classification. So and this is how sort of it would look in the World Reference Space. You see the cambisols and regosols here. This is an agricultural area. And histosols, of course, the bogs. You recognize the patterns. Okay. Then here a short summary, because it's interesting. If you know the Estonian soil codes, then here's an Madal, so Muld, and this is also a boggy type of wetland type, forested wetland, if I'm not mistaken, and of course glacials, are typically our clay soils here in Estonia. Okay, so but then the real challenge, because most process-based or natural science models, they work on soil texture, or very many, because the texture says the granularity of the soil particles, like whatever, like the little, granules. And again, we have also the situation that, of course, we have this very specialized, very well-described Estonian system. And in order to use models from the scientific literature, those rely on the international classification system called, from the United States Department of Agriculture, the USDA, and in FAO also. So, and in addition, as I said, these codes, they are so complicated, and this is because of the specific estimation of when the surveyor, the soil expert, the land surveyor, went to the field, and in each field they would either drill a hole or at least check the soil. So there was actually a lot of super surveying, like tens of thousands. So that's quite impressive. And so soil texture in Estonia, another situation is that Estonia used the Soviet system, which did only have sand and clay. So sand, for let's say for the normal layman, you would think sand is something really fine. But actually, sand is the coarser part of the soil particles, and clay is the really fine part. So, and in the here so-called Atterberg, or in the European or Western situation, you would say that there's also a silt, and silt is sort of in the middle. So, but the Soviet classification that we used here in Estonia basically only had sand or clay fraction, and then clay fraction, this is the diameter of those soil particles, like that. So that made it a bit more tricky, again, this direct mapping. So this is a very very nice handout from the University of Life Science. And basically, this, if, as a field surveyor without a laboratory analysis, this is how they would measure the soil texture. You know, and the finer it is, the better you can sort of roll it to a nice little sausage. Okay, so that's why you have a leaf, different leaves. This is sand, coarse sands, and then the finer it gets, it becomes here silty, loam, and then clay, savvy is the finest. So, and again, as I said, how those fine earth fractions, these texture classes, are described here. Then you have this is from the handout. Savvy, there's a couple more that also say which, like if there's gravel or limestone plates in there. So, and then we come here, Loimus, this is how it looks. So an expert, over the many years I've been working, I eventually became somewhat an expert to understand what that means. So there's a T here, and I think a number 1, that means this is a turva, so this will be a peat layer of 55 centimeters, and under this will be L, where the rest of the soil profile that was measured will be sand. So this way you have to it has to be interpreted, and in order to get all this information, that means this thing has 2 layers. The first layer is peat, the second layer is sand as texture. The depth of the first layer is 55 centimeters. So much information is within this one class. And it would be really great, of course, if we have this information available, which we now have. So because we have to somehow be able to analyze it, so I wrote a little more complex code, and that would then sort of extract it. So again, if we look here, we see what eventually this data structure came up with. So this first layer is an L here, so it's a leaf, you see, it's an L. It has 2 parts, so 2 layers. The first between 70 and 110 centimeters. So as SWAT, I have to go back to SWAT, also it's a bit more reliable in the international system, is in millimeters. I'm converting it here, so from 700 millimeters to 1,100 millimeters. So this is how this system analyzes this. And then the second layer, is LS, is leaf savvy, sort of somewhat eroded. And so this is how the system understands that. So as we don't actually have the percentage of the fine earth fractions, we have to come up with some numbers. So this is again some uncertainty, and I'm very happy to discuss this further and to improve that. Wow, the time is going fast. So in order to add the percentages for the fine earth fractions, there's this texture triangle, and based on the description, this is again here from Marie Curie from the University of Life Sciences, we would have then to go and say, okay, this polygon that was leaf, that might be in this area. So then we would give the sand, silt, and clay fractions in 5, 5, and 10% sort of. And because that's what we need for the numerical fractions. There's some trade-offs, of course. Again, the default profile depth is usually only sampled to 1 meter, so we don't know how deep the soil would be still below that. And in many cases, you only have sort of 2 layers, but without any depth information, then we would just evenly divide it. And yeah, exactly. So that's the most important. And this is how we then sort of mapped those numerical values based on this texture triangle. We would then say these Estonian fractions would have, these fine earth fractions, they would have these values, and then we would add the English, the USDA texture. So this way we got all this information into numbers and actual classes. And then there's something that's coarse fragments, like how much stone content or rock content is in there. So there's the as you can see here, this is V is, I think, some type of right now I'm not 100% sure, but 2 means that there's around 15% of rock here. Here says V Rautkivi. Here this is Rautkivi, and the indicator down here says the contains 10 to 20%. Of course, we can't have ranges, so what I did, I just evened them out, and then we can say this layer, the soil texture, then has this type finest fractions, and then this rock content has this type of texture. So all this information then comes together. So what is really interesting is, and really great, is that now what we have, that we can make a bit more generalized classes, because many models and analysis really needed in this type of format. And it's really great to see this extremely fine resolution of the available data. That's why I was like so keen to improve it and to really use it. Okay, and as I said, several assumptions, of course, are in there. Then some layers don't have any finite, they only have a soil skeleton, which is only the rock indicator. So, but this could also mean that these are those karstic regions in the northeast, for example, because there's literally only sort of rocky area, but the water can actually go through. This is something that I would have to consider for the hydrology. And then there's a couple of things regarding naming. So if it's per volume or per weight. And the texture values in T are actually turvas, but there's also T for Tollen, which is silt. So, but in most cases it is correctly passed out as, actually in all cases, because the Tollen classes, they are specialized in this program. After the many iterations of review, we got it pretty good. So, and then in order to predict additional variables, so at the primary, really important topic, soil organic carbon. So we have really great collaborators. So eventually we got a lot of samples from also ecologically and environmentally different areas from Estonia, from grasslands, alvars, from bogs, wetlands, forests, and agricultural soils. And so we all put them together and built a random forest machine learning model, which we also improved over time, because initially we probably overshot a little bit and some of the organic values were too high. But on the other side, it's really great that we have all in one, that we can now spatially consistently predict organic carbon. So this can now also be used, for example, experimentally, carbon stocks, because you have the depth, you have the number of the layers and the depth of the layers. Technically, you could also actually calculate absolute carbon stocks based on the carbon content. And just one interesting thing, so soil grids is another really great initiative that predicts various soil variables, also sand, silt, clay fractions, organic carbon, bulk density, etc. But they do a machine learning that goes all over Europe. And just for comparison, if we would aggregate soil grids for Estonia, we get a distribution of values like this. Whereas in Estonia, for ESTO, we have a distribution like that, because here it becomes really obvious that our bogs have, of course, really a large area and, of course, a high organic carbon content. And this whole thing was done as open source and using only open source Python scripting. This is all available on GitHub and on Zenodo. This is all linked. So a quick rundown of the variables that we have in this data set. So this is literally the list of variables. And here, as you see, those textures, those information, they're actually per layer. If there are several layers, n layers, it would say if you have 2 layers, then you would have Z1 and Z2 variables with values. And this way you can say Z1 is the depth of the first layer, Z2 is the depth of the second layer. This way, each polygon, all the information is encoded in one row. So all those different attributes are available for each polygon at depths, depending on how many layers are defined. So we also kept the linkage to the original soil map. So with this one, you can, the idea of the polygon, you can link it back to the original one, because for the research paper, we were not sort of allowed to, well, allowed. Several of those other parameters that we didn't use, we shouldn't sort of document and talk, describe, because bonität and Werf, those are historical values, but we didn't use them. And we don't have a good understanding of how valid they are still, sort of. So that's why they are not in this database, but we can link it back. Okay, and then there's a couple of things that we can improve, as always. So we also have a website, we have an email list, and we are really happy if you want to contribute, if you know somebody who has more data samples. We know, for example, there has been some comments that some of the world reference-based soil classes are not ideal. So now, unfortunately, Arnar Kanal, he passed away, and so he can't anymore explain some of his thoughts. So we work with Ala Astober from the University of Leiden, and we try regularly to reach out to Priya and to some other and Pelu Mayandos, and then to try to on a collaborative basis maybe to improve this data set. It so far is sort of a rocky road. Anyhow, particularly carbon is the hot topic, and so it would be really great, of course, to improve the model also. Yeah, and so here, as you can see, EstSoil-EH web.app. So we made a little web app as part of one of the projects, and this is has several layers accessible, and one of those layers is a vector tile layer. So in a way, it's a web map, like like WMS, a web map. You can just load it in. But then those tiles are vector tiles. They're not just images, but they actually have data. And as you can see, here are all the variables, literally, for all. If you click on one of those, you would get the actual data from. So there's no need to hosting a server like a GeoServer or something. This is pre-generated data, and you can just sort of load it or add it to a web map or something. So yeah, if you have any question, then I'm open for questions. You can ask me. So I would really like to acknowledge the colleagues that helped with the EstSoil-EH data set. So then I have actually prepared two more really short information on two projects that are now using or used EstSoil, and also which are geospatially GIS and hydrologically interesting, and because it's also some of my work, but they also can give a nice showcase of things that are possible in geospatial that I'm happy to explain further. So we had a project here, Dr. Evelyn Wimmer here from Department of Geography was the PI, and we calculated riparian buffer zones on a national level for Estonia. And so I was a bit more on some of the technical things involved. So Evelyn has written a report and shared it and presented with the government. And so this is with the ministry. And so this is all ongoing. So if you have any question, I would like to refer you to Evelyn also regarding this report and everything. So, but the base was Estonian 5-meter DEM, so really high, comparatively high resolution. And we needed a couple of factors like slope, flow length, flow accumulation, LS factor. Then we created a weighted parameter from flow length, flow accumulation, and LS factor. And we used those soil texture class from ESO because now we had those 10 base classes. And we used GIS multi-criteria analysis for a nutrient sensitivity or sensitivity to nutrient runoff to streams, mainly from agricultural, like fertilizers, etc. And what we did is we sort of subdivided Estonia in 22 processing zones, because overall this was quite a big of a processing and geospatial computing job. So what we did those 22 zones, and then for those hydrological things for consideration, we did those overlap zones. And in the end, then we could clip it back together, so we had a seamless hydrological view. And the idea is that with these weighted input factors, we could then create sort of mixed flow and sensitivity maps. And as you see, so this would be like a stream, and where those higher sensitivity values from this is sort of a hilly area, an Otepää area, comes down and reach the river, then you have higher risk areas along the streams. And that would mean in those areas they are more prone. That means here it would be advisable to have larger riparian buffer zones. So this sort of in a nutshell. And the process and the weighting in order to create this type of specific slope length that sort of really represents the flow of the pollution, because it's depending on various factors, and including soil. If it's sandy soil, then you have higher infiltration, so you don't have such a fast runoff towards the stream. If you have a clayey soil, then it's really fine and the water runs over it. So that's why the soil is so important to know. So this all together would be like this, and this we calculated this for all Estonia on a 5-meter resolution base. And as we talk again, we come back to hydrology. We do some modeling. So a thing nowadays that we should do if we do this type of modeling is sensitivity analysis. And because we sort of make this weighted model, but in a way we don't really know what the contribution of the different factors is in order for our model. So we don't also know the uncertainties sort of. So would, for example, in one area, a really strong slope or high long flow length, would that have an influence or not? So we don't know that. So, and for that we do sensitivity analysis. And FAST is one type. It's a really sort of acknowledged now robust sensitivity analysis framework. And it has sort of a number of parameters for this formula in order to calculate how many times you would have to run this model. Then you vary the input parameters, and then in the end, it can calculate the impact that the change parameters have on the output of the model. So what was really interesting for us to see, in a way it's expected and well understandable, but it's also important. So in the zone 21, which is the southern hilly landscape, that would be here, just south of Tartu here. Here you see that the factors have a more even influence, whereas the first one here is flow accumulation. And because we have those longer slopes, because we have more hilly area. So here this flow accumulation, because here it really starts to aggregate over the many slopes. So that's why this has a slightly higher impact. Whereas in the north, here in this zone 7, which is comparatively flat, LS factor has the strongest, but really strong impact, because we see there's almost no strong slopes. So the flow accumulation itself and the runoff, they're not long, so they can't really aggregate a lot of nutrients along the way. But the local sort of of the terrain, so this becomes the most important factor. So this way we can do this type of analysis. And as I said, we had these 3 factors that we were weighting in the model: the flow length, flow accumulation, and LS factor. And based on the parameters, that means we had to do around 490 calculations. And if you think now, we have the 5-meter dam for each of these big zones. This always needs a couple of gigabytes of RAM and takes a couple of minutes to process, and you have to do it like 400 times for each zone. Then it's of course computational sort of demanding, but we had, of course, the luck also that we can do it here at the University of Tartu High Performance Computing Center, the HPC Center. So that is actually quite a little interesting exercise. And then as you see, then here the PRIA, those are fields, and based on this sensitivity and this flow, as you see, something like that, then it would be advisable to have actually really nicely local actioned recommendations to increase the buffer zone only in this area to protect the stream. And then you can be really targeted. Yet, it is a very local approach, but on the other side, we could calculate this for all Estonia. There's a nice geospatial processing. I'm reaching my 40 minutes now. I try to make the last 5 minutes quick. Okay, and as I said, geospatial, cloud processing, and so on. The way we used those 22 zones, they are basically joined tiles from the land where you can download the DEM tiles, and the whole processing workflow was then built upon these merged tiles. And they are all really big geotiff files, and there's sort of a new standard in town, which is becoming really popular in the remote sensing community. So here's that's why I'm mentioning it to you, that the way satellite data is accessed now. So in the Amazon cloud and Google, there's some others, and then many geospatial startups and so on. They use this so-called spatial, here this STAC, Spatial Temporal Asset Catalog, to have a sort of standardized way of listing the assets. The assets are the remote sensing, the images, with associated metadata, but again, sort of for cloud native processing in ways that it can sit in these cloud buckets, in these cloud storages. So they only need to sit on some web server. There's no other processing server or something, or a login or anything involved. And the COG is a cloud optimized geotiff. It's just a way how the data is written within the geotiff, that those overviews, that you can really quickly understand which bits of the TIFF you can download. The programs, Raster.io, GIDA, they do this all automatically now, QGIS. So you can have directly linked your geotiffs directly from a web. You don't even have to download anymore, because all this logic works really nicely together. And so we did this also as an example, where we then uploaded all these big TIFFs. I mean, we didn't quite know how we should deliver those outputs. You know, we have like 15 gigabytes of TIFF files. Shall we send it as an email to the ministry? That, you know, it's probably not going to happen. But this way, we can sort of make them accessible in a really useful, sensible way. And it's really cute that this is a web viewer. A JavaScript can literally load the full geotiff. Well, not the full, because it doesn't have to load the full geotiff. So that is pretty cool technology. So, and then last but not least, as I finally come now to the point that this whole 2-year journey with EstSoil actually went to start actually modeling with SWAT. And of course, the original hypothesis was that we have this really cool, super high resolution, super local, observed, surveyed data. So it must give better results in hydrological modeling if you can use it, as compared to local soil grids that are somehow generalized. And for that, we built in the Pohjogi area, which is, you know, just here around the corner for you, an observatory around the corner here in Tartu, also around the corner. We built the same model with different soil data sets. And but all the other data is the same land use, Estonian land use, same DEM, and so on and so on. Same climate data, everything the same, except that the soil variables that we loaded in are from different things. And then we compared it, calibrated the model with different objective functions. And then again, we also did sensitivity analysis in order to understand what the impact of the different variables is, in which ranges they are, in order to maybe understand, you know, underlying processes or of the soil data set to the overall model actually is. Yeah, so this ugly map from my ArcSWAT setup. So you see, this is here the Reola station. Here, Puriyugi goes up to Emajõgi here at some point, and based on the TEM, etc., this is all the same subcatchments, little subcatchments here, and so around 30 to 40 subcatchments, and SWAT then discretizes within these subcatchments into so-called hydrological response units, HRUs, which capture then the local specificity, combinations of same land use, same soil, and same slope, in order to have actually eventually the units where you do the process-based environmental equations, which again get solved per each HRU, which are then contributing to the sub-basin and then accumulating along the stream. So that's what the SWAT model does. And so one of the very first not too bad modeling outputs here is for the time from 2003 to 2014 is so the green area, which is so-called sort of uncertainty development, or the 90% quantile of the best simulations. So it's around, I think, 2,000 simulations, where in the calibration you change the parameters always a little bit. So this is an automatic process, obviously, and then to see what the objective function that calculates the observed versus the simulated flow output, the error. And then the different objective functions have slightly different approaches, how to say how bad or how good they agree, the observed versus the simulated. So, and while in some areas the red one is the best simulation, and the blue is the observed, is sort of the reference data. So in some cases it agrees quite nicely, and then in others it does not. Sometimes we have a slight lag. So there's certainly something that the model doesn't capture. So, and then some things like snow cover, for example. So it is because it's actually quite an interesting little complicated subcatchment that has like one half sort of forest, the other one is agriculture, and then there's some wetlands in between. You have the floodplains towards Reola, and then you have the undulating slope, the uplands towards Otepää. So in a way, it's a really interesting catchment. It makes it also complicated, particularly for process-based modeling. So, and one of the preliminary results is if we use this coefficient of determination as measure of objective function, then the sort of the 10% of the best simulations, they give quite okay results here for Puriyugi, which is actually wrong naming, which is our EstSoil data. And then we have global soil data, and based again on the soil grids, different discretizations at different resolutions. So this is interesting. Here EstSoil comes out best, which is very nice. So, but then we have Nash-Sutcliffe is a different objective function that looks slightly different against the error and over time. And here, I mean, everything in this area is already quite decent. I mean, the higher is better. 1 is the theoretical maximum, similar with R2. But you can have negative values too. Then that just means they don't agree. But here we have that more than half sort of, you know, of the model explains the variance. That's sort of what we say. But here ESO doesn't look so good. So that is quite curious. And I also can't exactly say why right now, why this is different in the different objective functions. And in terms of uncertainty analysis, I've 2 parameters chosen, bulk density, and the next one will be hydraulic conductivity, because they are based on the predicted data. So they are actually quite a bit sort of off the original data. But so, and what we can see here, the colors are coded the different objective functions. That means in these experiments, how the variation of this parameter has an influence. So it's interesting that for some soils, the parameter didn't need to vary so much in order to give good results, and in others more. And sometimes the behavior is similar, and sometimes behavior is slightly different. This is really just a statistical look at how the change during the calibration in order to achieve the best simulations. And this is just another view of those here actually. And then for hydraulic conductivity, which is interesting, for EstSoil, we have very large variation. And the other soils don't need so many large variations. So this means that the hydraulic conductivity in EstSoil probably might not capture what is actually happening in the catchment. Also, you see, but what you see, because R says, in this case, the way the calibration works is that it is a relative change to the existing value in the actual data set. So, and actually here they all have a larger change. It's like 10% or something, but consistently the same, sort of in a way that they are sort of systematic off, whereas in an EstSoil it's a bit more chaotic, so that they have a wider spread. So this is something that could be interpreted, but now it really goes down to understanding, of course, the model, and at first also just making a good model that captures the flow better, and only then we can come to actually predict water quality, which would then go back to what we do actually for also the buffer zones, etc. So this is sort of all this how this all comes together in the end. Yeah, so it's really important to understand the catchment characteristics. And as I said, snow, we haven't really considered snow because the Ottepe slopes, they're actually northwards, so there might be issues in the delay of the catchment response. That is one of the thinking. And one important bit also to acknowledge always when we do those type of things, all models are wrong, yeah, but some models are useful, and this is really what this all is about. That's why it's good to sensitivity, uncertainty analysis, in order to understand where the model is most wrong, so that we can exclude this. It's not like the modeling actually doesn't say where the model is really good, so that we can rely on those top 10, this is where the model is really good. It rather says those other bits, there's the model really bad. It's an interesting thinking challenge. Yeah, and if you're interested in EstSoil collaboration, please look on our website, the landscape geoinformatics.utee. The paper, this is actually the preprint. The paper was just published like a month ago, a couple of weeks ago. The latest version of the dataset is available on Zenodo. And make sure if you go to Zenodo, it will tell you, because we had, as I said, different iterations. And we might have additional iterations again necessary in the future if, due to collaboration, we can make the dataset better. Then, of course, this is an open process. We would make this, of course, also publicly accessible. Thank you very much. Sorry for being over the time. I didn't guess that it actually takes so long, but it's super interesting. So, questions?
Thank you. I can see that Jan has asked about your first application and suggested some specific location to show on the screen. Can you share the screen and show that
I'm not exactly
location?
sure if I can find this exact location, but what we can do is I share my screen. I share my browser here. Where are we? Big blue button. Allow. Okay, here we have inception now. Then I go on EstSoil-EH web app. So what I can now do is I go on Google Maps. Google Maps. And I'll try to find this. Ach, Sonntag Flugstauer. Yeah. I can also send you the text from Sonntag. I still don't find it exactly. Give me a second. Sonntag. Where are we here? Sonntag is just under Würzburg. Okay, let's look somewhere there. So gotta be somewhere here, I guess. And vector tiles. So okay. So what's the question? What you can also do is here we put this button. You can go with your phone, and then we allow location access, and then it should. Okay, I'm obviously in Tartu right now, and in the city we don't have soil data, so we clipped that out. So you can, as you see, you can try that also. So let me go back down here. So is it probably here by the river, is it? Okay, and then so we can hear the red is mostly was quite deep soils here, 2 layers. Here's even measured 1.5 meters. Top layer would be sand and a lot of sand here. There's a bit more organic carbon here. And then the second layer is leaf survey, is silt loam. Does that help you? Like, I mean, this is the way you could. Okay, yeah, you're welcome. Are there other questions? I can show.
Like some people are typing.
Okay. Thanks, Jan.
But I would definitely like to thank you very much because it was really useful presentation, and I wondered that maybe I should somehow try to come and listen more all the seminars of geography department, because
Yeah, of course, you're most welcome. And then we are always happy also to if anyone has any questions, even just drop us also an email. We try to be very, very proactive and open. Thanks for the comments. Yeah, and I know that the observatory always find it also very interesting. We're always also listening a lot to your presentations, and I was also at the Rus user training, and it was really cool to have this hackathons with you. So I think there's a lot of potential where we sort of can complement each other. So I don't see myself competing with you. It's really I see a lot of potential for everybody to be more productive, to get really out of the science or the data what you need. Yeah. But I have to thank that I have the chance to present our stuff to you guys.
Yes, because for the remote sensing, it's the main big parts are geography and physics, and so actually even it seems like a larger community of
I would
using the
totally
data is
agree.
with the geography
Yeah,
background. So
yeah,
the
and
physics
it's
part should provide the data and geography use.
yeah, exactly. Yeah, that's right. And we also sometimes when we talk, you know, in the department or in the chair or in the working group, that and all these startups. I mean, it's a really great time right now. All these remote sensing startups. But I also see how they, you know, we could even make their work even more better just with a little bit more of, you know, GIS. Yeah, yeah.
Yes, and definitely it would be interesting to use more remote sensing data in Estonia for nature conservation purposes. I think this is something where there is still very much unused opportunities.
Yeah. Yeah, I guess what is interesting in terms of the use and the uptake of particular remote sensing data is there is this interesting divide a little bit. There's so much potential, of course, in the sciences to find things which are just also really, really interesting and important to know. But then you also really have the business streams that have a very, very different requirement. And because they're businesses, they seem to have more money, and so they can do more things. Which is sometimes, you know, sometimes feels a little bit like, damn it, maybe we should do more business stuff. But then we can do what we want. But then we still need somebody to pay us for that. So right.
Yes. I'm also wondering, we have here some people from Latvia, some people seem to be from Finland. How can you maybe type into the chat or to switch on the microphone to describe how the Estonian data set and available information compares with what is available in Latvia and Finland? It would be maybe more a question for some of the audience. Or maybe you, Alex, know something
Yeah.
about how common is by your knowledge how the availability of Estonian soil data is compared to
I
the
mean,
rest of the
compared.
world.
Oh, okay, this is a good point. So let's start from small to big. So for Estonia itself now, I mean, when I also started already to work with the National Soil Map of Estonia, it's a fantastic piece of data. It's this high resolution. There are some issues that we in the GIS community have sort of to acknowledge a little bit because the scanning of those paper maps, there's a couple of areas where people know that because it was literally originally paper and then had to be scanned. So if they were a little bit sort of off or stretched or sort of not perfectly aligned on the scanner, then the georeferencing would take them a little bit off. So there's some areas, for example, where people think that this could be up to 100-meter sort of slightly distorted, but like a bit off. But on the other hand, it's only 100-meter. If you look at the national level, but it's just because the detail is so fine. And like, what did I say? Like more than 70% or more than 3/4 of the units that are mapped are smaller than 4 hectares. So this detail is amazing. And compared with the Baltics, as the Baltics all have been under Soviet occupation, under Soviet rule for some time, part of the Soviet Union, they all had more or less some sorts of this soil surveying for agriculture. But as far as I now know, that in Latvia, I saw some good data already. And in Lithuania, it might only be, for example, only agricultural lands that have been actually mapped. But we think, because I think I saw the Latvian data set, it is very similar to the Estonian data set. And the origin is the same, sort of. So the same methodology that we used, that we described in our open access paper, is could be applied to those data sets and maps in order to also generate even more useful additional soil variables. So that would be possible. Then I know, of course, the US has the US, and I know also New Zealand and Australia, they have really detailed and also long time sort of data sets, really well developed. So, and then in several countries, I know there's varying levels of either quality, in terms that there's not much in it, that there could be more, or the resolution. And for example, in Germany, if I'm not mistaken, because there is this federal setup, so that each federal state has some of those things are at the federal level. So some counties or federal states, in Estonia that would be sort of the counties, have better data than others, for example, or some are you can't just download them, you have to sort of buy them, or you have to have like a business reason, sort of, and it's a bit tricky. But Finland, for example, I don't know. Yeah, Yanis, yeah. This, yeah, we just had recently a chat that is really good. Yeah. Mm. Yeah, I know this feeling, Petri. We also, so the hydrological modeling, the soil water modeling part, actually, before we even go to hydrological modeling, the soil water modeling part is also really tricky. And I think, so the situation we have also in Estonia right now is a little bit, as I mentioned, there have been a lot of field analysis over the decades, but we think a lot of that is sitting in some ministry or some sort of public research institute that they have sort of, I don't know what their considerations are. Maybe it's just sitting in some drawer, and they don't know really what to do with it, but they also don't want to give it out because it costs money to collect all this data. But we have now seen, particularly with this organic carbon data now, that some agencies are really nice, proactive, and they see the value. And I think one of the things we should do is, it's in a way it's lobbying, but not with this negative connotation. It's actually more sort of advertising, and in the end it's a win-win situation that if this data is made available, then all the uptake that can happen and the resulting products that can come out of it can add more value, sort of, that it initially costed to take those soil samples. We know that there must be like thousands additional soil profile lab analysis also sitting somewhere, and so far we haven't had the chance to get them. In particular, those models like soil water, we know that for example, here Ainkul, he does something for wetlands to measure hydraulic conductivity, even, I think, and we could measure and model those for peatlands in Estonia, which is then only peatlands and still not, and how this all, but machine learning maybe can help us at least to sort of extrapolate a little bit. Yeah, so if you want to test this water model on different data sets, of course, it would be interesting because we have this layered and texture data. Sure. Yeah. Get in touch. You can write me an email, or here's my email. It's not here, but I can write my email. It's pretty obvious. Yep. Cool.
Wonderful if the seminar is so useful for creating new contacts and collaboration.
Yeah, that's fantastic. Thanks so much for reaching out.
And are there any more questions from the audience? If not, then I think it's then I would like to thank you again for a really useful, good presentation. And
Okay, thanks very much, Leah.
stop the recording now.